Now, the second source of noise is known as the deterministic noise, and that's what we are looking at in this video. So, deterministic noise. What is this deterministic noise? Well, let us assume we fix a hypothesis set, right? So we have a fixed hypothesis set, and of course we have a target function, and let us assume that the target function is extremely complex. So it's like something like this. Right, a very complex target function. Now we can imagine that within this like fixed hypothesis set, we may have like one of the hypotheses in my set that can come really, really close to my F. So that is my like best hypothesis set. And let us assume data has, so the like F is complex and there is no measurement error. So no measurement error. Okay, great. Now, this has nothing to do with data right now, and let us assume that the hypothesis set, the final one, that the best one that we have is denoted by H of star, right? And so the optimal outcome, and so let us assume this is something like this. So this is my H, the final hypothesis that I come up with, and for any point, let me say somewhere maybe here, for any point X, this, if we keep like going up, maybe somewhere here it touches the target function. Now what we have with our hypotheses is this, and let's say this point or this hypothesis is given by H star because this is like out of my entire hypothesis set, right? And this is H star X. This is the point that I'm going to have, right? Now what's going on is that the actual f of X is here, and what I have, despite my best fitting hypothesis, is H star X. Now basically the part of the target function that's lying outside the best fit acts like noise in my data. So this delta here, this difference here is a source of noise. And this is obviously the second source of noise. And this here, this exact thing here is the deterministic noise. So deterministic noise can be defined as that part of the target function that cannot be modeled. That part of the target function, I'm just writing it by F, that cannot be modeled. Okay, so like if you think about the learning algorithm that tries to fit this noise will definitely make my H star X will go astray because it won't be able to distinguish between noise and signal. So that's what deterministic noise is. This is what deterministic noise looks like. Okay, so having said that, in both the cases, in both the sources of noise, whether stochastic or deterministic, the effect of both of them, like stochastic and deterministic, the effect of both of them together is overfit. So both lead to a similar impact on overfitting, rather, I would say. Now, of course, there are differences between the stochastic and the deterministic source of noise. If we regenerate these X values here, if we regenerate the data, for the stochastic case, you can tell that you will get different Y values, but in the deterministic case, you will get the same Y values again, right? Because it's not really the regeneration of that, but rather the point that I'm getting on the hypotheses that's really affecting that. Okay, so that's how, that's the thing. And in fact, we have a good kind of difference that we can write down here. So the first thing is that if we regenerate X values, let's say again, and so for the stochastic case, let's say S is the stochastic case and D is the deterministic case, right? For the stochastic case, you will get different Y values. For the deterministic case, you're going to get the same Y values. Right? Because remember, in the stochastic case, you have that randomness in that error part that is unknown. Now, the other thing is the stochastic error leads to deficiency in your hypothesis set because you are unable to model y, no matter what x you selected. And no one can model stochastic noise, right? So then again, the second situation is the stochastic leads to deficiency in your hypotheses, right? Because you're unable to model y. For the deterministic case, we can think that by choosing a complex hypothesis, so for the deterministic case, I can say that choose a complex H, right? And maybe you will be able to lower the deterministic error or the deterministic noise. However, no matter how counterintuitive this might sound, but this will lead us to going astray again. Because think about it, even if there's a little bit of deterministic noise, there's a little bit of difference in the hypothesis that you selected and the final target function, there is a higher like chances of going astray with a more complex hypothesis because more degrees of freedom. And so basically for the deterministic case, there is a trade-off. Okay, so these are certain aspects of the stochastic and the deterministic noise that we need to be aware of when we are looking at the problem as a whole. And regardless, like once we have the data, the hypothesis said the learning algorithm cannot do anything. We have like only one realization of noise to work with, and the algorithm cannot differentiate between the two types of errors. Okay, so let us like summarize all of this. And you have the stochastic noise here, the deterministic noise here. And as you can see, y is f of x plus stochastic noise. Again, y is the best hypothesis plus the deterministic noise. The source of the stochastic noise is our measurement error, and the source of the deterministic noise is the target function and the part of the target function that my hypothesis cannot model. What happens, like what is the result of remeasuring yfn? Stochastic noise does not change, but deterministic noise changes in this if we remeasure the observed values, right? But however, if we change the hypotheses, the stochastic noise stays the same, deterministic noise changes. So that's essentially what's going on. The stochastic noise will not change if you change the hypotheses because that's there inherently in the data. We have we have some measurement issues already there, and that doesn't really affect the stochastic noise that's there in my data. Okay, so like to summarize all of this, we have a single D, that's data, and a fixed hypothesis. So we cannot, as I said, the algorithm cannot really differentiate between these two types of noise, and then we have to deal with it. That's the like key takeaway, I would say. Okay, let's look at like both these types of noise through the lens of our bias variance analysis that we did some time ago. And okay, even before that, we wanted to summarize deterministic noise here again. And I think we've talked about most of it, so I would rather skip this slide because I think I showed this picture already. Except like a more practical overview this example is giving us. Let us assume we are trying to show this picture to like a 2-year-old, right? And versus this picture. So what this is signifying here is that it's easier to learn with this picture, and you will see that in most of the like 2 to 4 year old books and all, they have like a picture similar to this one. This is like capturing the essence of what an elephant would look like in terms of the weight, the trunk, legs, and everything, right? So it is like capturing all of that. This has like more intricate details, and maybe like for an adult, this one might be better. But just to kind of understand that this is an elephant or not, I would say that a simpler representation of that would be enough. So here we can visualize this as more of having a deterministic like noise. And although like a simple model was easily learned by a 2-year-old as compared to the intricate details that the left one is offering, but then it is there, right? So this is what this is signifying. Okay, so going to the bias variance analysis and the noise. And we have talked about it earlier, and we have talked about bias variance as a way of expressing E out. Now we will use this bias variance analysis as a tool to understand how noise affects performance in our models. Now let me quickly write down. The expectation for D is the data of E out. This is the definition, is nothing but bias, function of X, variance X. So if you remember, this term here is nothing but the difference between your final g of x minus f of x squared, and this is nothing but the variance of g of x. Okay, so what happens when we have noise in addition to everything else? By definition, E out of x is g of x, but we don't have the f of x, so we calculate it over the values that we have, and so minus y whole squared. But now because we have noise, my y is f of x, and ideally speaking we want like f of x here, right? But we don't have that, and so whatever the calculated value, basically that's what this is showing us, plus the error, right? So now we have y equals f of x plus whatever noise we have, and so I'm going to substitute this y here, and so I'm going to get g of x minus f of x minus epsilon whole squared. If we expand this whole thing here, what we'll get is g of x minus f of x whole squared minus 2 times the error, and then gx fx, right, and the epsilon squared term. Now we want the expectation, the expected out of sample error, right? The expected value of this. This is what the definition said. So if we take the expectation on both sides, right, the expected value over the data and then E out of x, if we calculate that, then this term stays as it is, right? This term is going to go to 0, right, if we are finding the expectation, because we are assuming measurement errors are independent of my target function, they are independent of my g or x, and they are random. So the second term is essentially going to go to 0 because this is the expectation of the epsilon. So if I'm going to find the expectation of this entire thing, this goes to 0. So now we are left with this, and how do we rewrite them and how do we interpret them? Let me go to the next slide and maybe right here. And so this is the expectation of E out x is going to be the expectation of g of x minus squared plus the expected value of this epsilon squared. Okay. So if you remember from the definition of bias and variance, this exactly here is nothing but the bias plus the variance, right? We've seen that before, and so this is that. Now, what happens to this expectation of my epsilon squared? Now, if the expectation of epsilon goes 0, then this is only the variance of my noise, right? So I can simply write it as sigma squared. That's what it is. So basically the expectation of out of sample, and let me rewrite it for like a more generic sort of case for E out, is nothing but bias plus variance plus this sigma squared. So what are all these? If you think about bias, right? Bias is really measuring how well you can do. So how well you do when you have like basically some hypotheses set. How well can you do with the hypothesis set? That's what this is telling us. So this is nothing but deterministic noise, right? This is my deterministic noise. Okay, so that's that. What is this sigma squared telling me? What is this the sigma squared term telling me? The variance of the stochastic error. So this is nothing but like the stochastic noise, because this is like my stochastic noise. By definition itself is the stochastic noise. Now we are left with this like variance term. Now, if you think about the variance term itself, it is actually impacted by both types of noise, like stochastic as well as deterministic, both types of noise. And so basically this is signifying or capturing the model's susceptibility to being led astray by the noise. So basically it has an indirect This signifies an indirect impact of noise. Indirect impact of noise, and is impacted by both terms, right? And how, like if you think about it, it depends on my hypotheses and my n. And you can really lower the variance if you increase your n. If n goes large, then the variance drops. However, you cannot do much about the deterministic noise and the stochastic noise in this case, right? So basically what this equation is telling us is that your error is made up of these, like this is the decomposition of your error. And so when you're trying to solve machine learning problems, you need to analyze this decomposition because it has its own challenges. It has you have these choices of what exactly are you trying to do in your model, right? So what is the goal of your model? Whether do you want a lower bias or do you want a lower variance and so on, right? So depending on that, you have to come up with the final edge and the final algorithm. Okay, so having looked at this decomposition sort of my out of sample error, let's really try to summarize today's lecture, which is important because this summary is going to help us in the next lecture. So first of all, overfitting is some issue. It's a known issue, right? So it's a known problem, I would say. It's a known problem. And then we looked at an aspect that really leads us to overfitting, right? And this is noise. Noise is something that cannot be modeled, which is an important aspect, and and it's always there, one form or another. Now we know that there are two sources of noise. Now, the question that arises is like, if this overfitting happens, can we do something about it? Like, can we do something about this? Well, the answer to that question is yes, and that's good news for us. And we should be able to cure this problem. And the quick cure to this problem is known as regularization, which we are going to look at in the next lecture. And basically regularization, the general idea is that get the benefit of a complex hypothesis set and apply the brakes when required. Like just stop using the complexity at a certain point because it's not required beyond that point. So that's what we are going to talk about in the next lecture. And then like in the future, we're going to also talk about another cure to this problem in a certain way that's known as validation. So validation is nothing but a reality check. So that's like when we start getting a very good E in, that's kind of suspicious because we might not be able to generalize. And so that's when validation comes into picture. So that's it for this lecture. And then in the next lecture, as I said, we're going to talk about regularization.